Hi everyone, welcome to the last of the tutorial parts of the physics transition work this year. Um, there's another session to come next week. I'll explain a bit about that in a moment. Um, Essentially today though, we're going to flip things around a little bit. So rather than do the tutorial first as we've done in previous weeks, and then the examples and the questions, I'd like to flip it round. So if you've not downloaded and had a look at the question sheet, do that first, have a go at it, and then come back to the video because we're going to discuss what you've found rather than explaining how to do something. Okay, so this particular session is going to bring these two what seemed like distinct topics. Hopefully, you've realised from the work you've just done, it's bringing it together. We've done a session on density, we've done a separate session on particles, and in this one, we're bringing them together to just look at the density of particles and what information that tells us about particles. Now, before we move on, just to say we've not asked for any of this work to be submitted at this point, and we're not going to do that today either. Next session will be a review piece of work that will be automatically submitted anyway. But your notes and the work you've done from these sessions, do keep hold of those. Have a little portfolio of your transition work so that we can review that when you arrive next year. And it will these are parts of the A-level course, so they will make part of your formal revision notes anyway. So make sure that you hold on to any notes and any work you've done from these sessions. The sheet itself asked you to look at two different materials. Could have picked any number of different materials, but deliberately picked ones that are famously dense, or quite the opposite in the case of helium, which has a famously very low density. We all know that if you fill a balloon with helium, it'll float even in air. It's got such low density. Similarly, its lead is known as being a particularly dense metal. I went for things that were like more likely familiar with that regards. There are lots of elements actually with higher density even than lead. The highest, incidentally, naturally occurring element being osmium, which density is almost twice that of lead. And obviously, helium itself not quite the least dense element. Hydrogen does beat it, but I went with ones that perhaps you'd be familiar with hearing. Point was actually to compare the values you got. Now, I'm not going to go through the entirety of the solutions that you've got that. I will provide the solutions as normal separately to this, but hopefully you've got numbers similar to this. It might depend a little bit on the rounding that you've done throughout the questions, but hopefully you've got values a little bit linked to this. So helium, 0.178 kilograms per meter cubed, okay, as the density of helium. Now, it's worth just pointing out here that we've got this under standard temperature and pressure, so pretty much your normal atmospheric conditions is what that means. We could increase the pressure of helium because it's a gas quite readily, and that would increase its density. And there's a number of things we could do regarding to temperature and the effect that would have on density. That's more year 13 stuff. We will look at that a little bit later on when we look at gases. But for now, just normal conditions, that would be the condition that the density that would get assigned for helium. And lead, considerably higher. Okay, as you'd expect. It's, again, is subject to conditions, slightly less with it being a solid. There'd be less variation in the densities of lead, but there would be certain conditions that could cause some variation in that figure. But let's just look at the two numbers, okay? And they won't be a huge surprise to you. Helium, a very, very low density. Incidentally, the density of air is just a little bit over 1 kilogram per meter cubed, so considerably less dense than air. Water is 1,000 as a sort of a general point for you to consider. But the lead there, a really, really high density. Okay, as I said, osmium, that's over 20,000. Iron we looked at in session 1, that was just under 8,000. So those sort of figures are fairly typical figures. Where this gets a little bit more interesting, though, and perhaps a little bit more surprising, obviously you can account for the material densities just by thinking about what's happening with the particles. In a gas, the particles are more spread out, so the density is going to be lower because it fills up a much larger volume than a solid would. But when we get to the atomic densities, that's where it gets a little bit more interesting. And one of the questions did ask, would these results surprise you? Helium's atomic density, the density of the atom of helium, 53,000 kilograms per meter cubed. So a huge number, actually, pretty much 5 times the density of lead as a material. And lead's atomic density, just over 20,000. Now, what this tells us, first of all, is the atomic density is always going to be higher than material density because the atoms themselves are separated, physically separated, so therefore occupy a little bit of volume. Okay, but it may well be quite a big surprise to you to see that helium has an atomic density higher than lead. That might be quite counterintuitive, but what you've got to do here is think about the structure of the atom itself. Helium is a small atom with only 2 electrons, which under normal circumstances would occupy an inner energy level or an inner orbital. Okay, whereas lead will have several energy levels, so the electrons actually occupy a lot more volume of the atom, and the electrons are occupying that volume without attributing much mass at all to the scenario. You'll see that in the solutions we've essentially ignored the mass of the electrons because to the 3 significant figures we were working to, they made no real contribution. So the actual atom of helium, physically, because it occupies a lot less space because it's got fewer energy levels under normal circumstances, actually much higher than lead, which is quite a surprising feature. Then we move on to the nuclear density. We get these enormous numbers. 3 times 10 to the power of 17 kilograms per meter cubed. So a massive, massive increase. And you might have, when you're going through that, probably thought you'd made a mistake as you did that. Now, what you should have also noticed is that for question 3, where you're asked to find the density of a nucleon, i.e. a proton or a neutron, you got pretty much the same figure. Now, to 3 significant figures, there might have been some variation due to the rounding, but essentially the density of nuclear matter is constant. Now, to say it's very high. That's because the protons and neutrons are all very close together. It's all the mass, essentially, of an atom, all occupying that really, really tiny volume. So when you really think about it, it's not a surprise that the density is then going to be high. There's no empty space or not much empty space there, like there is on the atom, which we'll discuss in a moment. But the nuclear density also ends up being pretty much constant. And while you might think, well, that is a surprise for helium and lead to have the same nuclear density. In fact, all elements have pretty much the same nuclear density, and it shouldn't be a surprise, really, because they're all just made of the same 2 things. Nucleus of an atom, protons and neutrons. The other conclusion it does lead us to, which is quite significant, is that protons and neutrons actually, they're separated by pretty much a constant distance. It doesn't matter if those protons and neutrons are in helium, if they're in lead, if they're in any other element. To maintain a constant nuclear density means that those nucleons must actually have the same separation regardless of what they're in. That actually tells us quite a bit about the force that holds a nucleus together, which will be one of the early pieces of work we look at how a nucleus holds together, when, as we know, the protons will be repelling each other in there, so there must be a force therefore holding it together, and it tells us, the fact that the nuclear density is constant tells us quite a bit about that particular force that we'll look at when we study this in further detail moving forward. So that should give you a little bit of sort of background on these things, and there are some surprising figures there. So not everything is as it seems, and this is why this work is quite important. It tells us a little bit more detail about the structure of things, moving below that sort of standard GCSE version of density, actually looking at the structure inside an atom, and then particularly inside a nucleus, which is where physics goes a bit further. The sheet did ask to have a little look at the limitations of the work. Well, the limitations here is chiefly, the main assumption was that we assumed that everything was spherical. Now, to assume an atom is spherical is quite a broad assumption to make. An atom wouldn't even have a defined outer boundary necessarily. To determine the radius or the diameter of an atom is actually quite an arbitrary thing, and can vary depending on the physical states, both particularly internally, of where the electrons are are physically inside the atom. In terms of the nucleus, the larger it is, the more spherical you can assume it to be. But if you think about helium with just 2 protons and 2 neutrons, if you've got 4 balls, trying to arrange those into a situation that makes a sphere completely, obviously that shape isn't really a sphere. So there are those considerations which do limit the measurements and the assumptions we made, which is partly why, for the values I've put on there, I've only put the nuclear density to one significant figure, because the assumptions actually cause quite a bit of uncertainty in the data itself. That just brings us to the last little bit to have a think about, that the last question on the sheet, which was how much of an atom is actually made of anything, and how much of it is empty space. We've said, and you'll know from GCSE, that virtually all the mass of an atom is concentrated within the nucleus. So all the stuff that makes an atom is there, and the rest of it is empty space with a few electrons occupying orbitals, energy levels, clouds, however you want to model it. That's something we'll get into later, but basically around the outside, but occupying very little volume in themselves because they're tiny and having very little mass. And most of the atom being empty space. That'll be something you've heard, most of the atom is empty space. But I wonder if you've really considered how much of it is empty space. Now, the calculation can be quite tricky, and the way it's done in the solution is to first work out the volume of the percentage that the atom that's actually the nucleus. That's easier because your calculator will cope with an answer, and it comes out as something along the lines of 1.5 times 10 to the minus 11% is the nucleus by volume, which means the rest of it, 100 to take away that, is empty. When you do that on your calculator usually just returns the answer of 100. Because it can't cope with the number. Done by hand, you can do it by hand, okay, you'll get something along those lines. So 99 point, and then a string of 10 further 9s with an 8 on the end. Okay, that percentage of everything is empty, totally empty. And that's quite mind-boggling, I always think. It's not just most of the atom is empty space, it's virtually all of it. Contains no matter at all. It's just empty. And if all atoms are basically empty, then everything is basically empty. And that's it's quite a sobering thought when you think about it. But it's also a mind-blowing thought, and also will hopefully start to trigger perhaps some feelings a little bit better than emptiness within you, and perhaps something a little bit more like, well, the curiosity. Well, how do these things hold together then? A little bit of wonderment and amazement. That's absolutely what we're hoping to achieve with this. And hopefully moving forward, getting ready for further studies next year, you are starting to feel a bit excited and a bit inspired. So I do hope you have enjoyed these little tutorials. I do hope they've just got you thinking a little bit about what physics will offer next year, and that you are really, really looking forward to it. As I said, next week, just a few questions just to check your understanding and see where we're starting off from. Other than that, have a fantastic summer. Thanks for engaging with these sessions. I do hope you've enjoyed them, and we'll see you next year.